Good morning, everyone, and welcome back to 3650. Today we're going to be talking about an exciting new topic, operating system kernels. So these slides are mostly going to talk about the computer boot sequence, which is important background information since that's what happens before the operating system kernel starts. And the reason that we're talking about this material today is as lead up for homework 9, where you are going to be modifying an operating system kernel in order to implement a new system call. So you'll be implementing this system call in the XV6 operating system, and this homework is going to be due next Wednesday. And that means that if you are going to submit the challenge assignment, challenge 2, on time, that will leave you with 6 days to complete homework 9. That's just how the extensions have worked out, and I would like to fit in everything this semester. So luckily this isn't the most difficult assignment of the semester, but it will take a little bit of effort in reading unfamiliar code and figuring out what you need to modify in order to add in this system call. I'll be going through some examples that should help a lot with that today, but definitely consider trying to make sure that you finish the challenge on time and get started on the new assignment as soon as possible. And then the majority of the assignment of the lecture today is going to be going through the XV6 operating system and talking about how would you add a system call to this kernel. So boot sequence. For any computer, this is true for most modern machines, be it desktop or laptop computers, cell phones, smart televisions, embedded or single board computers like a Raspberry Pi. They all have the same general sequence for what happens when you press the power button. First thing that's going to happen is that a CPU is going to turn on and it's going to run some software called the firmware. That firmware tends to be loaded off a sort of dedicated flash chip that's part of the system mainboard or the system on a chip setup. And that firmware can be replaced. It is software, but it rarely is. Upgrading your firmware is something that you kind of have to do intentionally. Now, that firmware is going to try to track down what needs to run next in order to get the operating system to run. And to do that on a desktop PC, for example, it'll scan through all the connected disks. It'll look for things like USB thumb drives plugged into USB ports. It'll figure out what disk is going to be the next step in the boot process, and then it will run another piece of software loaded from that disk called the bootloader. The bootloader is then going to, it will have been configured with all of the operating systems the computer is supposed to run. Most computers only have one operating system, so the bootloader will just immediately load that operating system. But if the computer has more than one operating system or more than one version of an operating system, or if there are multiple versions of that operating system available to boot from, multiple versions of that kernel, frequently because an upgrade just happened, the bootloader will allow the user to select which operating system or version they want to run, and then the bootloader will load that particular operating system kernel to continue the boot process. The operating system kernel is the code that is going to be running as long as the machine is turned on. It has access to the hardware, it has access to things like physical memory addresses, and it's going to be responsible for starting user space programs, which have to obey the normal rules for normal programs. Now, let's consider that sequence on a traditional PC running Linux as it would have in 2002 or 2005. So again, you press the power button, and the hardware, in this case, the CPU, maybe a Intel Pentium 4, is going to load the BIOS, Basic Input-Output System, which is the firmware for that style of machine. That BIOS is then going to scan all the disks connected to the machine for the ones that are marked bootable. Actually, it's scanning the partitions on the disks for the ones that are marked bootable. It may find more than one, and you can configure the BIOS to have some preferred order. Maybe it would rather boot off the CD-ROM drive than off a USB thumb drive, or maybe it's always going to boot off the first hard disk drive. But in any case, there's some order, and based on that order, it's going to pick a disk to boot off of, and it will load the bootloader off that disk. That bootloader is going to be something like grub, and then grub is going to be configured with the different versions of the Linux kernel, probably as the result of a series of kernel upgrades that are available. And if there's no user input, it'll pick the default one. Otherwise, the user will be able to select which one they want from a menu. And then the Linux kernel will start booting. And eventually, it will run the first user space process ID 1. In the mid-2000s, that would have definitely been a process called init. Today, on modern Linux systems, that tends to be a process called systemd, but it's still going to be process ID 1, and it's still going to be responsible for running the rest of the user space programs. And that's how PCs traditionally booted up. Now, another kind of computer that we deal with a lot is cell phones, and they, again, have a similar boot sequence. So I guess you have to hold down the power button to get a completely turned off cell phone to boot. And then the CPU is going to load the firmware. And we have an extra step here. The CPU, the hardware, is going to check a cryptographic signature on that firmware before it can run it. The firmware is then going to load a bootloader. Again, a signature check will occur. And the bootloader loads the operating system, maybe iOS or Android. And again, it's going to check a signature to verify that the code that it's running is the code that it expects to run. If any of these signature checks fail, the phone hardware is going to sort of soft brick. You'll have to do something exceptional in order to get that device working again. Maybe hook it up by USB in a development environment set up and manually reflash something, or otherwise you have to do something extra. Otherwise, it's not going to boot the system if a signature check fails. So that's how cell phones generally work. Once the operating system loads up, it's basically just like any other machine with better power management. Modern desktop and laptops look a little bit more like cell phones than they look like traditional machines, and they have another fun property. So when you actually press the power button on a modern, like Intel PC, it doesn't actually boot the main CPU. Instead, there's a second CPU called the management engine CPU, and that's the thing that turns on first. And it's going to load the secondary operating system called the management engine operating system, and this all happens before the main CPU boots at all. This management engine operating system is this opaque piece of software that we don't have a ton of information about. We know that it's based on the research operating system called Minix, at least on Intel CPUs. But that's going to run before any sort of regular code can run, even the regular firmware. And that management engine operating system is going to trigger the main CPU booting. Once the main CPU boots, it looks like a cell phone sequence. That main CPU is going to run the firmware on a desktop PC that's called UEFI nowadays, and it's going to check the signature of that firmware. The firmware is going to load the bootloader, check the signature. The bootloader is going to select and load an operating system, and again we check the signature. Again, if the signature fails, we get a soft brick, although on this sort of machine it's less annoying because you usually can just stick in a USB drive and boot off that. It's not as obvious how to fix a cell phone that has had a signature failure of an operating system or of a boot sequence component. But it's still annoying. If something goes wrong, your computer may refuse to boot. So this whole signature thing raises an important question, and that is whose signature? Who gets to sign these components of software on your machine and make sure that the machine is allowed to run them? And the answer is that usually two parties get to have the ability to sign these pieces: the device manufacturer and the operating system vendor. And sometimes those are the same thing. Microsoft sells computers, so they're sometimes both the operating system vendor, Windows, and the manufacturer of, I've forgotten what their laptops are called, but they're selling laptops now, so it's the same company in that case. Google ships Chromebooks and ships some Android devices. Apple, of course, is always both the manufacturer and the OS vendor for their devices. So sometimes it's just one company, but if you have like a Samsung phone or a Lenovo laptop, both the manufacturer and the OS vendor are going to get to sign the operating system that could potentially run on that machine. But this raises the question, why are we letting the manufacturer or the operating system vendor decide what software the machine is going to be allowed to run? And usually the justification for this that is provided is that it's a security mechanism, and it could prevent a rootkit or unauthorized boot off a USB device, and so it's helping user security. Although those situations are kind of rare, usually you don't get to install a like rootkit in the firmware of someone else's machine unless you have like physical access to their machine and get to like take a screwdriver to it or something, or at least spend a while like booting it in some special mode and playing in the firmware config. The more common thing that this actually does is it can prevent unauthorized operating system installs or modifications. And the whole idea of being able to like jailbreak an iPhone is the idea of working around this manufacturer requirement that these particular phones can only run authorized operating systems from the manufacturer. And so although it's sort of a complicated topic, and it's not 100% clear that there's even a general answer for exactly what security properties this provides, in enterprise environments or with Chromebooks, there may be some cases where having a signature deciding what software can run on a machine that isn't controlled by the user who's sitting in front of the machine, that might actually have some security benefits. But in other cases, it's not as clear that it has security benefits, and this isn't really a security measure for the benefit of the user who sits in front of the machine and uses it. This is benefiting some other party. So this is kind of sketchy, but this is how machines mostly work nowadays. The other sketchy thing that's going on here is that management engine CPU on Intel processors. So when you turn on an Intel processor, it doesn't actually boot up the Intel main processor right away. We have the secondary processor running code that is sort of black box code that runs before the main CPU even starts. We don't even load the firmware, the UEFI firmware, until after this management engine operating system has gotten the chance to boot up, run a network stack, potentially communicate with other machines. And this actually lets Intel machines have a really neat feature, and that is that they allow remote administration by like an enterprise IT department that doesn't care at all what software is running on the machine. You could install FreeBSD on a random machine in a conference room at Northeastern University or at some big company, IBM, or maybe some company that isn't a technical company, 3M, Minnesota Mining and Manufacturing, and the admins for that company or organization would be able to re-image that machine remotely using this management engine functionality and install the latest version of Ubuntu or Windows 10 or whatever it is that machine is supposed to have on it. And they don't even have to know what was on it before. They can just do a remote wipe. They don't even care about the firmware. They can do a remote wipe of the firmware. And that's potentially really convenient for that sort of large enterprise IT administration application. But it's not clear that this is a feature that I want on my computer or that you want on your computer. In fact, this might be a feature that you explicitly don't want. And for a while, it wasn't really possible to turn this stuff off. You could sort of have Intel claim that it wasn't entirely turned on, but this management engine operating system would run before the CPU even starts, and it would connect to the network. And necessarily, it's not even actually really running in firmware, it's running in read-only memory. So on the machines, it's not even entirely configurable. And so that means that it's necessarily, in order to provide the functionality it's supposed to provide, it has to be listening on the network for these sort of remote commands to do remote administration stuff. And I don't know. Not the greatest thing to have on every machine. So Intel machines definitely work this way. AMD machines have a similar mechanism. Some ARM systems have sort of a weaker form of it. ARM systems don't usually show up in the sort of deployments where there's a bunch of machines that are hardwired into a network and you have like a centralized administration thing. So they don't have the full remote administration functionality that the Intel AMT, Advanced Management Technology, implemented through this management engine supports. But this is still reasonably common functionality that at least all machines, except for PowerPC processors, off the top of my head, maybe some MIPS machines that you can buy nowadays, have at least pieces of this going on. Now, obviously, this sounds like a backdoor, and that's because this is literally what this is a backdoor. Just it's an intentional backdoor that is for large IT departments. But one thing that we definitely don't want to have be true is we don't want there to be security holes in the management engine. And every Intel machine since like 2008 has had this functionality, and there's been at least 2 major security holes that result in all kinds of like interesting complications. One of them looked like it was a remote code execution bug, but they managed to patch it in firmware so that it doesn't actually result in being able to do remote code execution, and that was only for like weird old versions of sort of like Skylake era Intel processors. In any case, that's probably enough going on about the management engine, but it's important to know that this sort of thing does appear in hardware, and therefore it sort of matters what happens before the operating system runs. Hardware can have issues. I mean, we know Intel hardware can have issues. There was the whole Spectre meltdown, zombie load, family of hardware security issues that we've had recently. The management engine is just another category of things that can go wrong in modern processors. All right, so with that, we'll start our story for what we mostly care about for this class at the bootloader. So the bootloader will have selected the operating system. It's going to load the initial piece of the kernel from disk, and then we're going to do a jump to start executing kernel code. And on a modern 64-bit Intel machine, Intel-compatible machine, AMD 64 machine, we start executing 16-bit code for backwards compatibility, just in case the operating system that you're running happens to be MS-DOS version 4. So that story will continue when we start looking at the XV6 code, but before we open XV6 code, I want to talk a little bit about what XV6 is. This is the operating system that we're going to be using for the homework, and the idea here is that the instructors at MIT wanted to teach a systems course, and they wanted an operating system to use as an example. There's a bunch of teaching operating systems. We've had teaching operating systems for decades that were designed explicitly as example operating systems with nice clean designs so you could teach a systems course. But the instructors at MIT thought those weren't real enough. We want to teach real stuff. But the real stuff is too complicated. Linux, just the kernel, is millions of lines of code. Any other option, like as you get more real, you get more complicated, and as you get simpler, you get faker. The sort of one trick that they noticed is that if you go back in time, operating systems get simpler. And there's one family of operating system that is still entirely applicable that you can go awfully far back in time for, and that is Unix. Unix is the basis of the design of the Linux operating system. Unix is a direct ancestor of all the BSD Unixes, which include Mac OS. And so looking at a historical Unix is a reasonable thing to do. So these instructors from MIT ported version 6 Unix, which was released in 1975 for the PDP-11 mini computer. They ported this to Intel 32-bit x86. So the operating system that we're going to be playing with is real. It's related to real operating systems that we still use today, but the design of the operating system isn't especially modern, and we'll see some eccentricities of sort of historical programming styles, historical programming techniques. They have translated it from the historical C programming language that it would have been written in to modern C, but only to like the extent necessary to let it compile and be reasonably readable in on a modern system and for modern readers. So yeah, next thing we're going to look at how to boot XV6.